And so we're recording to this computer, which will save it, and then I'll be able to post it like you might like to see it. All right. Hey, the first thing I want to do is just make sure that everybody understands, because I was working with my 101 students this morning, and it came to my attention that not everybody knows exactly what they're supposed to do before class. And some of that might be their inexperience with physics and the kind of things we're doing. Here is the Reading Quiz 7 energy lesson that you should have seen yesterday or Wednesday. I guess I posted it. And just to be clear what's expected, this video right here is supposed to be viewed before class, and that's the subject matter for today. And then, of course, you're supposed to read a couple sections in the book, okay, 11, 12, and 13 in chapter 2, and then come on down and take the reading quiz. And the reading quiz will either be right here or it'll be over in WebAssign, okay? And I had some technical issues with mastering physics and linking to Canvas such that didn't happen. And so they hadn't seen today's video in my 101 class, but I'm hoping everybody does view these things before, because obviously I'm just going over really quickly, asking about questions, and then we're getting right into working problems in groups, which is what I intend to do today. But I really do believe that's enhanced if you viewed these things, these videos before you come to class, okay? And so that's my my recollection. On that subject, then, let me pull up PowerPoint. And I never see in the recent presentations the one I want. There it is, energy today. We're talking about relativistic energy. And I do want to make one point. On Monday, there is, having said what I just said about watching a video, I'm not preparing a pre-lecture video for Monday's class. It's actually one of my favorite lectures to deliver in person. And, this has to be fun for me too. And so I like watching people's reactions as you show them something that they've probably never seen before. Now, you do have to read the book a little bit. There's a section in the book I'm going to ask you to read before you come to class Monday. So that may let the cat out of the bag. But when you see the math of how what I'm going to show you on Monday works, should be a little bit of, as a physicist, an aha moment for you. And so that's why I want to do that lecture live. So what you should be working on, I guess, is the homework, which is due in WebAssign on Wednesday. Since there is no pre-lecture video to watch, that should free up some time. And then, of course, there'll be the worksheet from today and the worksheet from Monday that'll also be due. So I'm sure there's plenty of work, but one less requirement for this weekend is watching a pre-lecture video, because we're going to do a more conventional class come Monday morning. All right, I just want to go to the summary page for today. I don't have any polling questions. Let me get to that summary page if I can find it. Summary page, there it is. That's the summary page. And I'm going to share my Canvas, or I was sharing Canvas. I'm going to stop sharing Canvas with you and share PowerPoint for just a second. And share that. And hopefully you're seeing this PowerPoint presentation with the summary. This is right out of the summary for chapter 2, if you're looking for it, okay? And you can see that the first equation there is what we did on Wednesday. It's the relativistic correction to that quantity momentum that Dr. Tex talked to you about for quite some time. And then the new thing for today are the equations for kinetic energy, okay? It's not 1/2 the mass times the velocity squared anymore. We're not in Kansas anymore, Toto, as Dorothy said in The Wizard of Oz. It's changed a little bit for us. And you can see total energy is not just the sum of kinetic energy and potential energy like it was in Dr. Tech's class, or wherever you might have taken your physics 1 and 2 classes, okay? We say it's now the sum of kinetic energy, and replacing potential energy is this thing called rest energy, or I sometimes say rest mass energy, because the mass and the energy are interchangeable, is what you hopefully saw in the reading in the video for today. And then the relationship between energy and momentum is not simply the momentum squared over twice the mass, which is equivalent to 1/2 mv squared if you just push the symbols around a little bit, is equal to kinetic energy. The relationship between energy and momentum is given there in equation 270, right? And so I did in the video a problem where you've got a kinetic energy given to you as 2 gigaelectron volts, and you work that energy into finding what the speed of the particle is, and you can figure out what the momentum is, and the rest mass energy, and the kinetic energy, and the total energy. And that's what you're going to be doing on the workout, on the breakout groups today, once with the worksheet problems, once I ask, are there any questions? And again, as opposed to me asking poll questions that normally might prod some, oh, I didn't understand that, your chance for questions before we break up into groups to work some problems. Give you a second. Anybody got anything? All right, good. So let me switch over to a different, go back to Canvas again, I guess. And let's see. Let's see, where is Canvas? Canvas, right there. Share that. And of course, there's the reading quiz. And I don't know how you find this stuff. Some people like to go to assignments. Other people like to go right to the modules. I've got it organized in the module. And I actually broke, you may have noticed, chapter 2 up because it's so long into 2 portions. Up to when we did twins in space-time, that was 1 portion. And then when we started talking about momentum and energy, and then what we're going to do Monday, which is electromagnetic special relativity, I created just another, I called it chapter 2A, basically. And so where is the worksheet? I'm hoping that's the right one. I posted the right one for you. Let's make sure. Okay, so calculate the rest energy of an electron, calculate the velocity of an electron, calculate the velocity of a proton, and then consider an electron with that kinetic energy, answer some questions about it. And so those are the 4 questions. And I'm going to, everybody have any questions on those? I'm going to break you up into 4 groups here once I can find the breakout groups. There it is. It put it over under the dots. We're going to make 4 groups, create breakout rooms. In room 1 is Prince and Sayed. You guys are working problem 1. In room 2 will be Anaya and Max, and you're going to do problem 2. Breakout room 3 is Amaya and Justin. And breakout room 4, doing problem 4, is Sam and Shneha. Okay, and so I'm going to open all rooms. Work your problem. We'll give you about, it's about 10 minutes or so, maybe 15 to work it. I'll jump around. Once we're back, we'll reconvene, and we'll go through what we normally do, which is go over the problems, and then we're done. One thing I did want to say, if we do that, you and Shneha, you were uploading them anyway. You can, you don't have to though. Just you get an opportunity to ask questions about them. But frankly, I'm writing down little grades as we're going through the problems, and then I just put those right in Canvas as your grade for classwork for today. So if you want to continue uploading, you want me to look at something, I will, but you don't have to. You don't have to upload them. I think Sam, you asked me this one time. You don't have to upload it. I'm sitting here grading it as you guys are presenting it. And also, you're doing one of the 4 problems, while the other groups are talking through their problems. You obviously want to make sure you understand, and maybe you write it down in your worksheet or in your notes or something, because of course you're still responsible for that. Remember, when you're briefing a problem, you're basically teaching the other 3 groups about your problem. Okay. Everybody good on that? Thumbs up, yep. All right, then I'm opening up the breakup groups. Again, Prince, Sayed, you're problem 1. Anaya and Max, you're 2. Amaya and Justin, you're 3. And Sam and Shneha, you're 4. Opening the rooms. Have fun. All right.
Just act like I didn't hear anything.
Okay, so can you see my screen? Oh no.
No.
It says started for me. Sorry, I just jumped in on you guys. It's trying to, it's just probably slow.
Yeah, I had it connected, but I'm just
I
gonna
think it
restart.
dropped. It's because I'm seeing you now. So, okay, there you go again.
Yep, restarting.
It's going on and off.
But yeah,
It's just
yeah,
blank.
the mirror just takes a little while. But before it starts, so we're talking about rest energy here. So rest energy is E naught, right, equals mc squared. I have a question. Like, how is this like even? There we go. So I have my notes on the left here.
Okay.
I was just like interested to know, like, because this is the same equation as Einstein's
It's this
equation.
big one, right? Everybody knows this one. Yeah.
Yeah, everyone knows this, but like, what makes this special that we call it? No, this is energy. Like, this is rest energy.
Because this one is rest and the other one is like E.
Yeah. Well, I think that before Einstein, people thought about mass as mass and energy is energy. And it may still seem that way to you, but I'm going to show you a physical phenomena where a particle with no mass, like a piece of light, creates two particles and they go off in opposite directions. Literally physically converts just energy and electromagnetic radiation into two particles. Before Einstein, nobody thought that was possible. It was like, what's that? And yet it happens, and it's something you can do in a lab. You have to get pretty high energy of light. I mean, you really got it, but you'll create something called, well, you know what an electron is. You'll also create a positron, okay, which is a piece of, and this is a weird
positive electron. Yeah,
it's an antimatter electron. So out of just energy in space, you could create two massive particles, okay? And before Einstein, nobody put that together. They couldn't figure. And so that's what's so profound about it. It almost was an artifact of the math, right? It just dropped out of his calculations. And then he kind of scratched his head. And this is, I think, Einstein's brilliance. He goes, that means that I can convert energy into mass somehow, or go the other way. I can take a piece of antimatter and a piece of matter, which have mass, and I can combine them together, and I just turn it into energy. It annihilates away. And we'll look at those phenomena. It's fascinating stuff. Does that answer your question?
It does. It does.
Yeah. Okay. Yeah, so now it's just a matter of doing the calculation, right? Do it in joules and do it in electron volts for us. But that's the significance. Other questions? Yep. I'm going to jump into the other group then.
Okay. So just a quick one. So like the rest mass is just showing us that we can convert energy between the two. So yeah, there's no like really any difference between the rest mass and the other mass.
Yes, yeah, you can add the other mass is sort of more kinetic energy, right? Or it's related to the momentum of the particle, like kinetic energy is. Those two things are a combined unit and can be shifted around, just like in Dr. Tech's class, you shifted energy from potential energy and it got converted to kinetic energy, right? That's how you did it. And now we're saying you can convert mass into kinetic energy, right? It's a pretty neat idea. But if you think about it, that's sort of what we're doing in nuclear power plants, aren't we? We're taking the mass of uranium, we're splitting it up, energy is being released as the uranium nucleus splits up, it goes away as heat, and then we're able to get useful work out of that heat energy. And so, and fission the other way, putting two things together, like hydrogen into helium, like happens in the sun, is taking mass and making energy out of it. It's pretty profound stuff, actually. And before, in the late 1800s, no idea about any of this. Einstein comes around in the early 1900s and solves all these problems, and all of a sudden our understanding of the universe blows up, doesn't it? Just blows right up. Does that answer your question? Yeah, this is the revelation of the last 100 years that really took us out of maybe the industrial revolution into the way we live today with lasers and computers and nuclear power and all these things that are in the last century of the world. Pretty profound stuff. And this is just the beginning, right? You're doing the first piece of it, which is doing a calculation or two. All right. Other questions?
Okay.
All right. I'm jumping.
All right, thanks.
You bet.
Hello.
When you square the left side, I got, wait, what did I get? I got a really big number. Let me try to make it simpler. 4.93 times 10 to the
10 to the.
it's +9.
All
If
right.
I'm doing my
Hey, I'm gonna jump in and make your life easier, I hope. Okay.
Okay.
Please do.
You know, to some extent, can I write on this? Let me see if I can write. Annotate, yes I can. There's my little thing. This guy right here isn't the way I would use it, okay? I wouldn't use that mass because that's gonna make a lot of trouble for you. And I think this number right
We're
here.
getting weird numbers.
Yeah, what'd you use? What'd you get right here? Where's that number from?
This is MC squared.
Okay, what are the units of that?
This should be, I think it's
Kilogram meters
I
per
think you're in
second.
joules, aren't you? Yeah, you're
Yeah.
in joules.
Yeah.
And over here, you've got EV. So you've got a dilemma there. Now, you could solve it one of two ways. You can either convert 2 MeVs to joules, but and that's certainly one way, because right here, you need to have the same units, don't you?
Yeah.
And you don't. Okay, so you can either convert this to joules, the 2 MeV to joules. I think it's easier, and just because I've done the problem, to make this, we said the mass of an electron, it keeps putting my name right where I want to write. I'm going to try up here. Yeah, there it is. I don't know why it was, now it's put my name again. Equal to, it's identifying who's writing. But we said the other day, 0.511 MeV over C squared. Okay, that's the rest mass. And so you can see when you multiply it by C squared right there, this term right here just becomes 0.511 MeV, right? And then when you go to divide it out into the 2 MeV, well, your units are much nicer, aren't they? Okay, you could do it the way you could go to joules too, but yeah, yes, that'd be my recommendation. All right, I'll leave you alone to finish. I think that'll make your math come out, but the bigger issue is watch your units, right?
Yeah.
You're
So you change the mass instead of kilograms to the rest mass.
Yeah, well, they're both rest mass. They're just rest mass in two different unit systems. Okay, these are both rest mass. All right.
Gotcha.
And you could choose to use whichever one you want. I think in this particular problem, 0.511 MeV per C squared
way better.
is way easier. And I didn't finish. It's per C squared, right? And by the way, both of them are there's a little chart in the front cover of your textbook. So if you go all the way you scroll all the way to the front of your e-textbook, you'll find that. And if you don't have it, I actually have a handout that just has the constants from the front cover of the book. And you just have that available as a PDF document to open up. Okay. Hey, one more thing before I leave. Am I saying your name right? I know I feel like I'm massacring your name like people massacre my last name. Am I getting it close anyway?
It's Inaya.
Inaya. Okay. Long E. Got it. I'll get it. My apologies.
Fine, yeah.
My apologies.
No, cool.
All right. I should at least make an effort. You've been in my class for 2 years now, or 2 semesters now. So I got to
Last semester, I swear you were saying it right.
Was I saying it right? And then I just forgot over the summer? All right.
Yeah.
Long E. Inaya. How'd I do there? Better? All right. Inaya.
Like an I in there.
Long E, long I. Yeah. Okay.
Yeah.
See you guys later.
Okay.
See ya.
Thank you.
Thank you.
let me see what you got. Okay. Hey, how you guys doing this morning?
Okay.
All right, so I'm looking at what you did. You got gamma mc squared minus mc squared is equal to k, yes. And so you used for the proton, mass of the proton 938 MeV per c squared, good. And gamma minus 1, so you divided by mc squared. 200 divided by 938. 0.213 plus 1 is 2.1, is 1.13 then, right? Okay. And now you still got 0 right over here. 2.1 plus point, that's a point right there, right? Let me annotate what I need to do here. Annotate. So when you add that up, don't you get gamma is equal to 1.
There's a c squared, right?
0.213.
But there's
So,
a c squared in the denominator, right?
hold it. No, that canceled, didn't it?
There's another c squared here as well, right?
Yeah.
There's oh my bad.
Yeah, so
Oh, I got
it's
the
K, the kinetic energy, divided by mc squared, right?
oh, I got the units wrong over here.
Yeah,
I
okay,
took it
gotcha.
as ME,
All right.
yeah.
Yeah, I think that'll make your life a whole lot easier, actually, I think.
Yeah, it would.
Yeah, so then the math will, you should have that. I think the result I see is that gamma should be 1.213.
1.2. Yep, and then
All right,
yep.
I'll leave you guys alone to finish that, and I'll go on to group 4. Any other questions?
I don't think so.
Jump into the other group. Yeah, you did the smart thing, which is use those units of mass for that proton. So we'll jump out of here.
Yeah, like you get
That's
a
what's
few
not
things
making.
here and there, but oh.
It's kind of confusing for me. Like trying to check it, I'm not sure if I should like.
Okay. No, hey, I'm here now, so I can bust in on you. And I
What do you
agree with
think?
your answers to both A and B. Let me
Okay.
make sure. Okay, I bottom line numbers I agree with. Let's make sure I agree with kinetic energy. Yep. So, and by the way, if you care, just because you went into MEV units, which are obviously the better units in my mind. Had you done it in joules, 2.42 times 10 to the minus 13 joules. Okay, so
Yeah.
you could see why 1.5 roughly is a whole lot better unit. And then yes, you subtracted that off, right? So you took your answer from A, squared it, subtracted off the rest mass energy of an electron. Okay, squared divided by c squared. You got the square root of, and that's 1 point. Yeah, and so I guess
The part that gets me is trying to distinguish c squared as a number and c squared as a unit.
yeah, it fills both roles, doesn't it?
I get kind of confused doing
Yeah,
that.
well, you did it right here. If you the answer, I guess, let me pick my annotate, is if you're going to use that, it just was there, right?
Yeah.
So you just slide it from right here, where it's actually in the calculation, to right there where it's in the unit. And this is the point of unit analysis. If you're always doing unit analysis, it's in one place or the other, right? By the way, if you left it right there, well, then the product of momentum squared and the speed of light squared has units of energy, right? Either joules or MeV. And this, what you did right here, allows you to define momentum units of energy divided by the speed of light, right? Does that, I don't know if that
It's
helps.
just,
Yeah,
I think it's
easy.
just a new unit. I just haven't learned it quite yet.
And you guys aren't alone. I can tell you, this being the 3rd year I've taught this, if the earlier you can get this idea though, just get comfortable with it, the more the next sets of problems we do will be easier for you. Because one of the hardest things I found with previous students, they always tried to go to kilogram meters per second for momentum. And you can, it's fine, but see how easy your problem was compared to try to get everything out of MEVs over to joules in order to have momentum units a kilogram meter per second.
There's so much back and forth work
You
in
would
a
have had,
calculator
yeah,
or
you would,
something.
yeah, exactly. And so because of you, first you had to convert joules to EV or EV to joules, I guess. There's that conversion factor. And then you've got to no kidding put in 3 times 10 to the 8th meters per second. And then you got to no kidding square it, right? And the odds that they were able to, students who didn't do it the way you did this problem were able to not make a mistake somewhere in those calculator manipulations became like maybe 10, 15% that they came out the other end with a correct answer. Whereas you didn't feel good about it, but you got the correct answers because you just accepted it. And the calculator manipulations weren't that bad for you folks. So yeah, just get used to it. Other questions for me?
I don't think so.
Yeah. Okay. I think the other groups, we had to correct a couple things. You're actually a little ahead of them. What time we got here? It's funny about Max.
12.
Yeah, this one was pretty straightforward.
Yeah,
so-
pretty straightforward. So we're right at. Yeah, it's actually I'm in
Yeah,
Central.
are you I was wondering if you were an hour behind.
Yeah, I'm an hour. I had to get up for 7:30 for my class this morning at 8:30. It was reminded me of being at the Naval Academy. A little better for you all, but yeah, we got about a minute. It's about a minute after 12, and so we'll just give them a second or two to make sure their groups have finished, and then we'll come back and we'll show everybody our answers. You can erase. Well, actually, why don't I erase my stuff just so it doesn't interfere when you're showing everybody how to do your problem? And
Yeah,
I
I didn't
appreciate.
know how I could do it.
Yeah, I don't think you can. I think you're stuck. The question though is when we go back out of breakout. I'm erasing it right now. Are
I
you?
can too. If I
Okay.
draw this and you were to draw something, it says clear all drawings, and I could
Okay.
leave it there.
Yeah. All right. That's. It's funny. I'm learning more and more stuff about this Blackboard and the Notability. I don't know if they're useful skills moving forward, but they are skills. All right, I'm gonna go check on the other groups. We'll be ending up this group in a second. Any other questions? You can show everybody how to do this problem?
Yeah, I think so.
Yeah.
And make sure that the discomfort you all felt about what's these units, make sure that you emphasize, hey, this is the way to do it, because it would have been really hard to do it the other way. One of the corrections I had to make on another group is they had units of joules for one energy and units of MEV for the other energy, and they tried to add them up. And I'm like,
Yeah, that's bad.
go back to doing MEVs and C-squareds and all that. You'll like life a little better. So, all right, jumping out of your group here.
All right, thanks.
Okay.
You bet.
Thank you.
Let's go back to those guys. All right, so let's see. I'm back here to just kind of check your numbers because we got and you went to meters per second. Remember, you can always go with a beta times C if you want. The one issue, I guess, what do you think about that number for your velocity? Any concerns with it?
Oh, it's 10 to the 9th, which
Yeah,
is
that's a little bit of
faster
trouble,
than
isn't it? Yeah.
speed of light.
You need me to erase my junk too, don't you? Let me erase my stuff here. So I'm trying to figure out where your math issue is. Let me erase. I don't know if I can erase that stuff anymore. I'm trying to. All right, so let me see what numbers I agree with. You had, all right, so 2 MeV. This is just gamma, right? Okay, good. You can erase my old notes. Excellent.
Yeah.
So this is just gamma right here. But then, oh, you're missing the rest of the equation. Yeah, the 2 MeV is kinetic energy. So this is minus mc squared. So
okay.
right here, there's a minus 0.511, right? And my advice is just keep this so this becomes gamma minus 1 times 0.511 MeV, right?
Yeah.
And so right here, I guess, is that +1 or -1? Let's see, 2 MeV. Yeah, I did it in one step right there, but I have gamma is equal to 4.9. And I'll leave you guys with that. Gamma equals 4.91.
All right.
All right, so when you get to that, then work from gamma's 4.91, work it on out. All right, go into another
Makes
group.
sense.
You bet.
Thank you.
All right, where do I go? I got a breakout room. Max.
And it basically ran numbers.
So for you equated the first one and
Yeah. So this is this, and this is that.
but so my question is, if you have KE and the rest mass, then can we just use both of those to find the total mass? Like just add them together?
You can, but like you can find the total energy. That's what you can find if you add these together. But you're trying to find you know, that that's
Which is buried
we're
in
not trying
gamma. Yeah.
exactly. Yes.
Hey, can I check your numbers for one before we go back to get everybody together?
Sure.
Oh yeah, we got 0.0017 electron volts.
All right, hang on. I'm looking at your first one. 9 point. All right. I'm just, okay, so 3 squared is 9, and then 9. I have to check my numbers because I'm not getting that number. Do me a favor, put your 9, that's 9.11, 10 to the minus 31, and put it in, multiply by 3 times 10 to the 8th squared, because I'm not getting your number.
Okay, I'm gonna double check. Okay.
Yeah, double check that.
Oh no, you're absolutely right. Wait. It's
That
interesting.
is 2.73 times 10
Did you
to
get
minus
this,
22.
Professor? Did you basically get this?
Where am I looking? Hang on.
The second question.
Yes.
8.2. Yeah.
Yes,
So
that's
I
the
don't know
number I
what
got.
we did wrong. Yeah, I don't know what we did wrong there, but
Yeah, I
maybe it
think
was
I know what you did. I don't think you squared the speed of light.
exactly. No, I think that's it.
Well, because you kind of look at it, 9 times 9 basically has got to be about 81 and just move the decimal point. Yeah. And it's actually 82, right? But the decimal point moved.
Very true.
And
wait,
you see what I'm saying about 9 times 9? You got 9.11. Don't try and do 3 digits. It's just 9. And then 3 squared is also 9. You know the answer has to be somewhere around 81, right? It's just
Right.
kind of a hint on checking your math. And that's just a protection against not squaring something. Okay, so you're good with that.
Absolutely.
And then you just have to change that. Yeah, exactly.
Perfect. Yeah.
Right.
I'm gonna get it done before we
Now,
get back.
that said, I agree exactly with your number 2. 0.97 is your speed. 0.97 times C. I actually rounded
it's great stuff. It took us a second to realize it because I was using the normal rest equation and then I was getting an answer like twice the speed of light. I was like, what is this?
Yeah, and only because I think we did it slightly different. I rounded it to 0.98, but I think your math, we agree on all your numbers other than that. It was just how you uncovered the velocity out of gamma. And that's just a round off error, I think. All right?
Absolutely.
Go check
So,
on
Professor, I'm just gonna give you this answer. Is it
that looks good. Yep. There you go.
Mega electron volts.
Perfect. All right, and that should be a familiar number because that's the rest mass of an electron. If I divide it by c squared, right?
If you divide it by c squared, what do you get?
You get the rest mass of an electron in that units, right? So what we say then is the rest mass of an electron is most people carry it out to a third digit, 0.511 MeV over c squared, right? And so you just kind of prove that constant. It's now a constant you can use forevermore because you just proved it, right? Okay.
Yeah, that makes a lot of sense. Yeah, for sure.
Right.
Let's head back. Yeah.
Yeah, I'm gonna. There's one other group that they keep messing up their problem. So you guys are done, and I'm gonna go check on them and see how they're doing. See you in a bit.
Perfect.
We'll end it. All right, you guys fix it yet?
Almost.
All right. Yeah, the other groups, I think you guys are the last one. So once you got this fixed,
So 8.49. .21 times 10 to the 8th.
That sounds right. I actually have it. So let me do a quick piece of math here. Hang on. Because I want to divide it by C, because I want to give it like a beta times C. So let me see what, divide yours by 3 times 10 to the 8th. Tell me what fraction you get.
All right.
Let's see, it'd be like, up, you know what, that can't be right. It's still greater
Yeah,
than
no.
yeah, so you're still greater than
Let's-
1. You still got a math error. You know where your math error is, I
Ah.
think? I think that should be a 4.91 right here.
4.91.
Yeah. Because when you take right here, and here's why, I see it now. This should be 2 plus 0.511, right? Because when you bring this 1 to the other side of the equation, right, it's 1 times 0.511. And when you bring it over here, then this, you're yeah, it's gamma squared, right?
Yeah.
Yes, that is gamma squared then. Okay. Yeah. So it's that same old extra term right here that you dropped. All right. Hey, I'm going to jump out here. We'll give you about another minute, and then I'm going to jump back into the full group so we can talk about these. So
Okay.
one more minute here. We'll see you guys later. All right, you guys are back. I'm waiting. I think the other groups should be here in just a moment.